So the third and final implementation we're going to look at is FileCounterParallelStream. As you might think from the name, this is going to apply the Java Parallel Streams framework. And you'll see it's much more concise than what we looked at before. So let's go ahead and walk through it. You can find it in this file here. So we're now going to take a look at the FileCounterParallelStream class implementation. It does the same thing the other ones do. They all provide the same results. It extends abstract file counter. It has a public constructor that takes the entry point file, and it has a private constructor that's used as part of the recursion. And let's take a look at its compute method. Its compute method starts out just like the other two. There's no real change for the basis of the recursion. Is the file a file? If so, increment the document count and return the length in bytes. If it's not a file, it must be a folder, or what we sometimes call a directory if you're a Unix programmer. And what we're going to do here is a little twist on what we saw before. This is super cool. So check this out. We say stream of, and we take the list of files, which is really an array of files, as we talked about before. So we convert the array of files into a stream. And now we do something magical. We say dot parallel. Dot parallel is a directive to the stream's runtime framework to split the contents of that list in such a way that they will all be capable of being run. All the different files at that level in the folder hierarchy will all be capable of running in different fork join tasks that are internally managed by the framework. You don't have to do forking. You don't have to do joining. It handles it for you. And so this will make everything run as a parallel stream in one simple call to this little factory method. And then what we do is pretty much identical to what we did before with a couple of important twists. Notice how we use map to long, which is this intermediate operation that will take a parallel stream of files. And for each file, we're going to go ahead and create a new file counter parallel stream, passing in the file, passing in the document count, passing in the folder count, which are the atomic longs. But unlike what we did before, we don't call fork here. We just call compute, because each of these things is going to run in a separate fork join task managed internally by the Java Parallel Streams framework. So we don't have to do a forking. The forking goes away. We just call compute, but now it's going to run in a separate thread. And what's cool about that is after all those things are done processing at that level in parallel, we then use a terminal operation that sums the results up and returns them. So I think you will hopefully agree with me that this code is much simpler to read and write once you understand how to read it. And it's definitely simpler to write. There's less stuff to write. We don't have to fork anything. We don't have to join anything. Remember the first two examples we looked at, you had to do forking followed by joining. First we did it with Java 7, object-oriented looping. Next we did it with Java streams, but there was forking and joining going on. Now all the forking and joining is pushed into the parallel stream framework, and we can just focus on describing what we want the solution to be, and it handles all the details of making that solution run in parallel efficiently on our multi-core platform. So super concise, super cool. Of course, the remaining question is, how do these things perform? Is there one that's faster than the other? Is there one that's slower than the other? And that's what we'll look at next.